All right, so we are talking about viscous flow, which means now, right, we're fully embracing the fact that fluids have viscosity and they have viscous losses. And we're going to start with looking at flow in pipes, internal flow, in particular, fully developed laminar flow in pipes. So we've talked about this several times, the transition between laminar flow, which is steady state, smooth, right, dominated by viscous forces, into transitional flow where inertial forces start to become more significant and they produce some transitional momentary instances of chaotic flow, and as that transitional flow becomes fully turbulent. And in all this transition in this direction is a result of Reynolds number, which is equal to rho v d over mu, increasing, right? As it increases, we see this transition from laminar to transitional to turbulent. So we're going to focus on laminar today, but I want to talk a little bit about what laminar means in terms of Reynolds number. So this d here is a characteristic length. And that changes based on every situation. So a wing, it's a chord length; a pipe, it's a diameter; a ball, it's its diameter. But it's like a flat plate, it's the length along the plate, right? And that length is some characteristic length, which is important for the flow, but it's different for every situation, and therefore we cannot directly compare Reynolds numbers between different situations. But we can compare, for example, the Reynolds number between pipes, because pipes are the same situation. We have a long cylinder and we're flowing fluid inside of it. And so in this, we can say for a pipe that roughly around a Reynolds number of 2100, and this varies based on conditions such as the conditions of the pipe, any vibrations, conditions of the entrance, right? We'll talk about the entrance here in a second. Anything lower than this is laminar. We have a transition region between there and about 4,000 of transition. And above that, we have turbulent flow. Now, again, this is a rough thing. I had a professor when I was in school who for their doctorate, they were measuring laminar flow in pipes and trying to see how high of a Reynolds number they could get, how far above 2100 they could get and still maintain laminar flow. And he had to do his experiments at night because people walking by in the hallway outside the vibrations produced by them walking would trip turbulence within his system. So vibrations are important. All these little things are important. So all that to say is it's not like there is a hard number. It's not like where you're 2099 and then you switch to 2100 and suddenly now you have transitional flow, or the transition between 3,999 and 4,000, you suddenly get turbulent. No, these are soft numbers, but good guidelines. And why does the entrance matter? Well, if we look at these two entrances for our pipes here, and we draw our flow, and remember we've talked about this, but flow coming around a corner, when it enters the pipe, we've got a big area here, and it tries to come around this corner, but it can't make a 90-degree, right? Fluids cannot do 90-degree turns unless they're going incredibly slow. So it misses this turn. Its momentum carries it past it, and we get a narrowing at the exit here, which we actually talked about when we did conservation of linear momentum. This is just like our reentrant exit for our tank, how the exit is narrower than the actual diameter of the pipe. And then eventually it spreads out. But we get lots of chaotic recirculation region here, and the same thing happens on the bottom. Get a recirculation, wrong direction. Recirculation region here, and eventually this spreads out, and we get nice flow here. If it's laminar, we'll get a nice parabolic flow. If it's not, we get something else. But this time that it takes for this flow to even out again after entering a pipe is called the entrance length. We'll call this entrance length. Yeah, called entrance length. And it can be as small as 1/6 of a diameter, or it can be as large as 120 diameters. It can take sometimes quite a long time for the entrance length for the flow to fully develop, is what we would say. Fully develop into a profile that does not change as we move along the pipe. So one of the things we can do to reduce this entrance length is to, as you might expect, ease the transition of the fluid into the pipe. So if the fluid slowly, if we curve our entrance, we come like this, then almost immediately the flow is already ready to be the, oops, I didn't draw that quite right because I was talking, is ready to be in the flow profile that it wants to be, and it reaches equilibrium quite fast, and it doesn't take very long. So sharp edges mean longer time for it to reach an equilibrium, longer entrance lengths that are maybe 120 times the diameter of the pipe. And generally, we can say that for laminar flow, the ratio of LE over D, right? Note this is a non-dimensional number. So if we go back to dimensional analysis, LE over D is a pi group, if you will. We can say that this is equal to, for laminar flow, 0.06 times the Reynolds number. So as we increase our velocity, the entrance length increases, right? It takes longer for it to reach equilibrium. The same is true for turbulent flow, although to a lesser degree. A curve fit, if you will, for this. This is an empirical formula, but 4.4 times Reynolds number to the 1/6 power. Still, as we increase our Reynolds number, it takes longer to reach a equilibrium and get a stable profile. So for very fast flow, it can take, like I said, 120 pipe length diameters. So let's draw now exactly what we mean by flow profile changing. When we enter a pipe, flow comes in like this, and it starts off actually looking very much like what we call plug flow. So this flow has what we might say is a flat topped profile. All the flow is going at the same speed. Now, obviously, the flow very near the surface is moving with zero velocity because it's no slip condition. So it's stuck motionless, but we have a very high velocity gradient here. High gradient, which creates very high shear stress, tau, very high tau. And that shear stress starts to slow down. It slows down this fluid right next to the wall. And the slow fluid starts to move inward. So if we move a little bit down the pipe, we see that we have maybe less of a flat top, like this, right? The flow near the walls the slow flow near the walls has spread, and the flat top in the middle is a little bit smaller region. And then as we move down, again, if we move even further, we might actually reach a region where we have a nice parabolic flow, where the influence of both of the walls has completely spread. And we'll talk about this more. These are called boundary layers. The boundary layers grow, which is the influence of the wall, like this, until they intersect. And where they intersect is where the fluid now has the viscous effects of slowing down the fluid have fully spread throughout the pipe, and our flow profile will be the same no matter what moving forward. And this is the entrance region here. Entrance region. So, by the way, what is this flow profile? This is a Poiseuille flow, and it is a parabolic flow profile. We've looked at it a couple times. So let's look at the forces on a fluid element real quick, and see if we can predict if we can calculate this flow profile. So if we have a flow in we forgot to draw our pipe. Let's draw our pipe here. We have flow in a pipe. So here's our pipe. And let's actually let's not use this. Let's draw a radial profile. So this is Z and this is R. Then inside of a pipe, we're going to have three forces on our fluid element in the middle of our pipe. Here's the middle of our pipe. So the first forces we're going to have is pressure gradient. So we're going to have P1 times pi R squared on this side pushing in this direction, and on this direction, remember, because pressure always acts inward on a control volume, but we've kind of drawn a control volume here. So we have P2 times pi r squared. Now, why do we have two different pressures? Well, we're looking at viscous flow now, and remember, as we move down the pipe in this direction, we lose pressure due to that pressure energy becoming heat, right? Pressure energy becoming heat. And that the thing that's causing that pressure energy to become heat is a shear stress counteracting that pressure in this direction of tau times 2 pi r times L, where this is the whatever the length of this pipe is. So if we sum all the forces on this object in the x or the z direction, we find that this is equal to m times az, but this is 0 because we're steady state. We're going to assume steady state here. Nothing is accelerating. And this is going to be equal to P1 times pi r squared minus P2 times pi r squared minus tau times 2 pi rl. And this is all equal to 0. So if that's true, we can cancel out all the pi's. That's great. Cancel out one of the r's. And we find out that if we rearrange and divide by, this is equal to P1 minus P2 times R minus tau times 2L. And we can rearrange this a little bit further, and we can say P1 minus P2 over L is equal to tau times 2 divided by R. This, by the way, is our pressure gradient. So if you, well, we didn't really do Navier-Stokes this year, but in general, this is a pressure gradient where we might say this is delta P over L, which is usually equal if it's constant to dP dz, right? Or down the length down our pipe. And the right-hand side is our shear stress. Now, we know that tau is equal to some constant times our radius, right? Our shear stress. And we know this because it's 0 in the middle and it's a maximum at the end. And we can actually solve for this. We know that it's tau is equal to some constant times the radius. So that isn't particularly useful, but we also know that tau is equal to mu times du or d du sorry, let's see, dw dr, right, where w is the flow, direction of flow in the z direction. So we can plug that into here, and we get that delta p over L is equal to 2 mu over r. And we have it pointing in the negative direction here. I don't know where that negative came from. Oh, there's a 2 mu over r times du dr. And we can solve this differential equation. And if we bring r over to this other side, we get delta p over 2 mu L times r dr is equal to du, and therefore we get delta p over 4 mu L r squared plus c is equal to u. Now we got to solve for this constant. We got to solve for this constant here. And luckily we know that at the wall, sorry, W at the wall at R is equal to big R is equal to 0. So if we plug in big R here, we get delta P over 4 mu L big R squared plus C is equal to 0. Therefore, C is equal to delta P big R squared over 4 mu L. And we can rewrite this now as W, our flow in the Z direction down our pipe, is equal to delta P over and over 4 mu L R squared times 1 minus R over R squared. And actually, traditionally, this is written in terms of diameter, just because pipes are given a diameter. So delta P over 16 mu L D squared times 1 minus 4 R squared over capital D squared, where D is equal to the diameter of the pipe. Great, so now we have a expression for the flow profile, and it's parabolic, 1 minus R squared. So this is a parabola. So we know that this flow profile, if we had a pipe here, the flow profile is going to be parabolic, the maximum in the center, like that. Great. Oh, that was the next answer here. Flow is a parabola. This is also called Poiseuille flow, which I don't know if I can spell, but we're going to give it a shot. I think there's 2 S's. Spelled Poiseuille flow. It's French. It's a good term. So this is all great, but we usually don't actually care about, for pipes, the flow profile in a pipe. What we care about is the flow rate, Q. So Q is equal to the integral of W dA, integral of our flow across our area, right? And our area in our pipe is going to be this whole circular cross-sectional area here. So we have to integrate this flow profile across this cross-sectional area, which means we have to use ring integration yet again. So this is integral from 0 to capital R of W 2 pi R dr, which is equal to, pulling all our constants out right off the bat, we get 2 pi delta P times D squared over 16 mu L times the integral from 0 to R of 1 minus R squared over D squared. Well, you know what? Let's take that D and let's make that D a capital R, just because that things will cancel out nice if we do that. Capital R squared R dr, which if we integrate, then we get, and we cancel these out, it becomes 8. We have pi over 8 delta P D squared over mu L times R squared over 2 minus R to the 4th over 4 capital R squared, evaluated from capital R to 0, gives us that Q, well, we'll just plug it in right over here. This is equal to Q, remember. Q is equal to pi D to the 4th delta P over, and then this is huge, but 120, oops, not 180, 128. 128 mu times L. So, and if we really want to get spicy on this, we can add gravity to this force balance up here. We're not going to go through the derivation, but if we add gravity to this whole thing, we get pi times delta P minus rho GL sine theta times D to the 4th all over 128 mu times L. And what does this tell us? This tells us that the flow rate in a pipe, Q, is proportional to delta P, which makes sense. If we double the amount of pressure, we would expect to get, for laminar flow, this is true, by the way, this is only laminar flow. If we double the pressure, we get double the flow rate. That's awesome. What's really interesting about this is the response of the diameter. If we double the diameter, we get 16 times more flow for laminar flow than we would if we we get 16 times more flow by doubling the diameter, which is crazy. That means flow rate is highly sensitive to diameter. And then, as we might expect, if we double the length of our pipe, we would half the amount of flow rate. Half the amount of flow rate. All right, let's do a quick example problem here. we want to know what is the flow rate in this pipe. We have water at a height of 10 meters. Let's draw our X and Y. We're going to draw our coordinate system right there. We want to know what the flow rate is in the pipe. So we have this water draining through a 2,000-meter long pipe with a diameter of 1 centimeter. That is quite low, right? Quite a small diameter pipe and quite a long pipe. And so we are going to now plug stuff into our equation. So our equation we have for flow through a pipe is that, and this is pipe at an angle, so we're going to have to include gravity in it. We have Q is equal to pi times delta P minus rho G L sine theta times d to the fourth divided by 128 mu times L. Awesome. So we know that the pipe leaves at P atmospheric, but we don't know what the pressure here is at the front. So we're gonna have to figure out what this delta P is. So we need to use hydrostatics here. So we have to figure out what this pressure is here, which we're gonna have to use rho G H. Now, hydrostatics assumes non-moving fluid, but fluid is clearly moving here. So we're gonna assume steady state at constant properties in order to be able to use rho GH. Now, I think you guys remember me saying this before, we can use anything we want and we can assume anything we want. We're stating that we're assuming steady state so that people understand that we are assuming that the movement of the water is small enough that it's not going to affect our answer significantly. Now, what significant is varies based on the application. We're doing a problem for a class. Significant is 3 sig figs, right? NASA, when you're flying to Mars, significant is probably 5 sig figs or 6 sig figs, right? You want to be dead on when you're trying to do these things. So yeah, we're assuming steady state. So our P here at the front, P here for equation 1, delta P is equal to rho GH. 1 to 2, we have delta P is equal to 1,000 kilograms per meter cubed times 9.8 meters per second times H, which is 10 meters. So delta P is equal to 98,000 pascals. Great. So now we can plug that into here. Since and we get that our Q is equal to pi times delta P plus rho G sine theta times d to the fourth over 128 mu times L, which we go to the next page, we can plug in all of our numbers and we get that Q is equal to pi times, this gets boring, but 98,000 pascals plus 2,000 meters times sine of 10 degrees times 9.8 meters per second squared, all times the diameter, which is 0.01 meters to the fourth, divided by 128 times 1 times 10 to the third, negative third Pascal seconds, which is the viscosity of water, times 2,000 meters, which is the length that we're experiencing here. So we solve for our Q and we get that our Q is equal to 2.76 times 10 to the negative fifth meters cubed per second. And this corresponds to an average velocity. VAV equals Q over A, which is equal to 2.7 times 10 to the negative fifth meters cubed per second divided by pi times 0.01 squared divided by 2. VAV equals 0.351 meters per second. So it's quite slow, right? 0.3 meters per second. And let's calculate our Reynolds number now. So our Reynolds number for this flow is going to be equal to rho VD over mu, which is equal to 1,000 kilograms per meter cubed times our velocity, which is 0.351 meters per second, times our diameter, which is 0.01 meters. All that divided by our viscosity, which is 1 times 10 to the negative third Pascal seconds. We get that our Reynolds number is equal to 3513, which is transitional flow. So remember, this formula we just derived for the flow rate is only valid in laminar flow. So transitional flow is getting close to where, this is close to 4,000. I don't know if I would trust this. I don't know if I would trust this flow rate. I don't know if I would trust this velocity. Yeah. All right. And that's that for this lecture. Next, we're going to start talking about friction factors and how those can help us use this information in our conservation of energy equation.